and share the slides. Okay, hold on. Okay, can you see the slides? Okay, good. Right. Okay, this is a review class, the final class for this course, ZAT386. So I call it a review class. But normally I do this class before the final exam, so I can recap all the important things that you have to know, and you have to prepare as the gist of the course, as the essence of the course, and also mainly for your final exam as well. But since we don't have any final exam and you have finished your test too, let's just recap anyway to at least reflect on what you've learned. Okay, this is not for exam purpose, but rather more on you reflecting what you've learned so far. Okay, so we have gone through classes together for about 15 weeks, and we've done all the assessments. So you've completed your assignment one, which is a single assignment, and then you have completed two tests, open book. First one in the first half of the semester, and second one yesterday. And then you've also completed a group presentation, okay, last week. So this is the main thing that you have to ask yourself, or you have to reflect. So if you are given, say, 1 minute maximum, how would you summarize what have you learned in this course? Anyone? Amirul, maybe you want to summarize in like 20-30 seconds. What have you learned in this course?
For me, I learned the basic principle of semiconductor, the type of semiconductor, and how it works. And
okay, all right. So how that's the essence. So that's pretty much about. Okay.
And I learned a few things about the mechanical on how electron move in the semiconductor, the recombination, the SIV, all the new thing. I think it's for me is I learned all new thing.
Okay, all right, that's good. So that's like 30 seconds more or less. Okay, anyone else? What have you learned? If you can summarize that in under 1 minute. How about Rafai? Let's just recap. It's okay. What have you learned? What do you think you've learned so far in this course for the last 15 weeks, more or less?
So I have learned so far, actually it's too many, but the most important or general thing is about we learn something theoretical such as the PN junctions, such as the metal semiconductor or principle of semiconductor, and then all the theories we apply to the real life and into the devices such as MOSFET, such as LED, such as many things. So all the theories we learn, so we apply to the device that we are going to use in making the big devices, such as handphones, such as computer, and all the devices are connected together and to form the big one, such as a computer, handphone, and everything that related.
Oh, Faris, host. Ada apa benda nak cakap? Silakan.
Okay, Faris, ketua kelas. Ada apa-apa nak cakap?
Okay, sorry all. Can you hear me now? Suddenly I was disconnected. Can you hear me now? Okay, sorry. We need to find okay, okay, tadi tak dengar, you cakap you nak start je, saya dah disconnected. Can you go over again? Unmute, you are unmuted now. Sementara saya buka slide ni, you just go ahead and share. Okay, yep.
So far what I've learned, all the theories that we have learned, such as we learn about the metal semiconductor, Schottky diodes, PN junction, and everything about the theories that related to the semiconductor, and then we learn also about how all the theories we applied to the certain devices, right, such as MOSFET, such as BJT, such as LED, and so far and so on. So at least we know about how the device operated, so that we applied to the real one. So I think it doesn't have any problem because we know the theories, a little bit about theories, and then for now we are just to know more about the real one, on how we use all the theories that we have learned into the devices that we are going to create, something like that.
Okay, that's good. Okay, all right. Any other summary? Let's go. Tengok nama ni. Oh, anyone would like to summarize? Juaria? Before we go to the slides, we can summarize in under 1 minute.
For me, I think I learned a lot of semiconductor, and it's good to have not so many calculation variables too much on this course.
Okay.
On the application, on the devices, on the PN junction, electron, proton. I love that kind of stuff that I can imagine instead of just putting the formula. So it's a really good course.
Okay, all right, okay. So, okay, there's like 30 seconds. So, have you, now do you know how to make sense of the calculation into the real application? Can you relate now? Others? I think learning physics, I think in the previous 1-2 years time are mainly about calculation, right? Quite a lot of calculations, right? And now can you make sense of the numbers? Juaria, can you relate now the numbers to the actual effects or operations?
Not entirely, but some of it, yes.
Okay, right. So physics is about making sense of the numbers. Okay, kalau you tak bagi, it's like you have the numbers but you don't have the roh. Okay, you don't have the spirit, you don't have the meaning. Physics is about giving meaning to numbers. Okay, kalau tak ada meaning means it's just like math. You see numbers, but you know it's really abstract. Kalau you can give meanings to the numbers, you understand what does it mean. Then it's physics. Okay, at least to my interpretation. Okay, Mac, anything you would like to say under the hoodie?
Pendek lah tu. So
Yeah.
what I learned about this course is I know about the fundamental of the semiconductor and the application of the semiconductor in our life. So I think it's improving our it make easier lah for our life to get a better service such as the solar cell, the light from the laser, and so on lah. And
Okay.
I think it's this course is more about the fundamental more than the theory.
Okay. All right. Okay. Okay. Thank you. So maybe any last one. Fatin Nur Tahira, would you like to say something? Go ahead, Fatin. Oh, the meeting. Okay, all right. Okay, last one. Siapa ni? Seri? Anything, Seri? Seri Iziani? Seri ada? Seri, come on, last one. Siapa lagi ni?
Hadi
Go
say
ahead.
one or something.
Hadi,
Go
okay,
ahead.
Hadi. Okay, Hadi, go ahead. Okay, come on, Hadi. In 30 seconds.
Okay, Doctor. Assalamualaikum. Thank you for teaching us for semiconductor. And I learned a lot of things in this course,
welcome.
like application of PN junction, what we do that in our solar LED, and more in semiconductor. I see more focus about how why we must I think the physics is just about learn how to can move, but here we learn most about electronic. That's this in part, I think.
Okay, so now I believe you can relate already most of the fundamental principle we have learned, right? The mobility, the generation, recombination that we learned in the first part of the course, right? So by applying the principles into the devices. Okay, let me go back to the slides now and let's go for another 20 minutes more or less to go through the content of the review. Okay, let me. Okay, you can see the slides, right? Okay, good. So that's pretty much the summaries from few of you. I believe the rest have also learned pretty much the same thing and pretty much have the same impression and reflection on what we have learned in the last 15 weeks. So let's recap the learning outcomes that we discussed in the very first class of this course during week one, not week, yeah. Week is standard. So week number one, I presented last time in the first class that at the end of this course, students should be able to first explain theories, characteristic of material, and operation of semiconductor devices. So this is the first thing you should reflect on yourself, whether unknown theories, characteristics of material, and eventually of semiconductor devices, which is related to P01 or A. And then the number two is you should be able to solve problem involved in semiconductor devices. So you have done quite a number of calculations when we learn about the physics and when we learn about the device. We don't have time to really go to rigorous calculations, but I only managed to show you some important examples. Okay, some of the important examples that you have to deal with when dealing with calculation related to semiconductor materials and devices. Okay, so this is more of a P03, which is related to thinking and scientific skills. So you have to do a lot of analysis and analytical thinking in order to solve the problem. And the same goes to question number 3, for example, if you talk about test number 2 yesterday, when you are required to compare the operation and the device of FAT, okay, so you have to have some understanding of the principles in the different device. Number 3, present operation of devices config 04, which is related to ratios. So we have done this in your group presentation in the last 2 weeks. Okay, so where we used to talk about 40, 50 minutes and then up 1 hour, including Q&A for every group when you got to the rest. So it's just an online platform, but I believe you've learned something from this presentation, which is not mainly on the communication alone, but rather on the teamwork, on the discussion, on negotiations, and knowledge while extracting important information from online. Okay. So during the first class, we thought of from the coursework, but a couple of weeks down the line, we just discovered that we couldn't do that because of the COVID-19 still prevails. So we then have to resort to 100%. Just checking if you can hear me and see me. Oh, sekat-sekat eh. Okay, can I? It's not so good this morning for whatever reason. Hold on, yeah. So is it okay now? Can you hear me? Okay, is it okay? Okay, right. Line fluctuate now. I'm sorry about that. Yeah, I have to go back and share. Okay. I hope you can see the slides now. Then we resorted to 100% coursework, and that's based on 30% assignment and 40% of test 1 and 2, and a group presentation that contributes about 30% of your coursework mark. So we started off by learning about basic of semiconductor materials. We learned about resistivity and conductivity of different materials, covering metals, insulators, and semiconductors. Then we learn about the crystallinity of different crystallinity of semiconductor materials, which range from amorphous polycrystalline to single crystal, or just called crystalline sometimes. Okay. So you learn about doping, you learn about how to take semiconductor material, and then how to dope the intrinsic material to make it N-type, to make it P-type. So for silicon, for example, you learn that you need to add on group number 5 or group 15, like phosphorus, arsenic, antimony, into the silicon to make it more N-type. And you need to add impurities from group 13 or group 3, like boron or gallium or aluminium, in order to make the silicon P-type. So you can then modulate the conductivity or the resistivity of the semiconductor material. So then we learn about the band diagram. We learn about the conduction band, the valence band, and then the concept of band gap for 3 different types of materials: metal, insulators, and semiconductors. So we learn about Fermi-Dirac distribution function, and then you learn about the basic equation on the Fermi-Dirac distribution function. So the probability to calculate the occupation of electrons or holes at different levels of energy in the band gap. And then you also learn about the thermal excitation by increasing the temperature of the semiconductor to above 300 K or above 0 Kelvin, for example, and see more and more carriers are excited into the conduction band for conduction. So we then move on to calculation density of free electrons or free holes by using the concept of Fermi-Dirac distribution function Fe, and also NCE or NVE, which is the density of states of electron and holes, right? Then you can then calculate the density of free electrons or free holes by using this equation. And then we learn about law of mass action, NP/Ni squared, for intrinsic, for N-type, and for P-type semiconductor material as well. We also learn about degenerate semiconductors. That will happen if your N0 is more than your NC, right? Or your EF is more than EC for N-type, and the opposite for P-type, okay? Then you learn about transport, carrier transport phenomena, and we learn about these 4 important equations, 2 for drift and 2 for diffusion. And drift will take place when we have electric field in the system, and diffusion will take place when you have concentration gradient in the system. And then we move on to learn about the concept of excess carriers. So we learn that we can generate excess carriers in our semiconductor materials by optical excitation, by electron bombardment, and also by doping. So we learn about generation and recombination as well. So one way to do the carrier generation is by light absorption. So you learn about the concept of indirect band gap and the concept of direct band gap, and how these affect the light absorption and eventually the light emission from your semiconductor materials. So we learn about recombination that can take place by 1 or more mechanisms in the semiconductor materials, which are by band-to-band recombination, or also called radiative recombination. And it can also happen by trap-assisted, or called SRH, Shockley Ridge Hall, and finally Auger recombination, which happens when the semiconductor material is heavily doped to above 1017. We then move on to PN junction before we started discussing about our semiconductor devices. So you learn about this energy to X or distance band diagram combining homojunction PN semiconductor materials. And you can see the mechanisms involving the drift and diffusion of both electrons and holes. And then you also learn about the bias junction and what happens to the carriers when you increase the bias or when you reduce the bias. We learn about the concept of minority carrier concentration at the end of the depletion region on the opposite side of the junction. So you learn that when you implemented the junction, you can see increase PNB or NPA on the opposite side of the depletion region due to the bias. We then move on to learn about PN junction under illumination. This is more related to optical or optoelectronic devices like solar cell, photodetectors, and some other devices as well, which involve light excitation in order to generate carriers. Then we move on to contacts after finishing the PN junction. So we learn on the role of contact, which is to extract carriers from the junction to the outer circuit in order to complete the circuit. So we learn about the concept of Schottky and ohmic. So we can design the type of junction, metal semiconductor junction, by choosing the right work function of the metals in comparison to the semiconductor material, which can be either p-type or n-type, and we'll end up with rectifying or ohmic contacts. Then we move on to heterojunction concept in terms of the band diagram, in terms of the combination of material. We also learn about lattice mismatch and how do we reduce lattice mismatch by doing the calculation of the lattice constant from both semiconductor materials. And then for the device, we first learned about solar cell before we started your group presentation. So you now know the device configuration of a typical solar cell. How does it look like? And then the operating principle of a typical silicon solar cell. We then discuss about MOSFET. So you now know that there are 4 types of MOSFET. We have P and N type, depending on the channel type, which is here. So you can also have enhancement mode or depletion mode. So for enhancement mode, you need to apply the right voltage with the right polarity at the right level in order to turn on the channel or induce the channel. And this is the concept that we use in the device, which is called field effect transistor, right? So you need to induce the right voltage in order to induce the field effect, which induces a channel formation by the inversion layer concept and stuff like that. On the other hand, for depletion, you need to apply the right voltage with the right polarity in order to turn off the channel, because the channel is already there due to the fabrication process. Okay, it's already embedded in the device. So you learn about the IV summaries of the 4 different types of the MOSFET. Then we learn about the CMOS concept, which combines NMOS and PMOS in an integrated circuit. So, well, firstly, you learn about the concept of NMOS on its own and then PMOS on its own. But when you talk about integrated circuit, it's about integrating or combining both PMOS and NMOS to do multiple functions in the device. So you also learn about MOSFET scaling and why is that required. So we have related that to Moore's law, which is an observation rather than a natural law observed by Gordon Moore back in 1965, when he learned that the density of the transistors will double every 18 months or every 2 years. And that's still happening until today. Even though today we are talking about Moore's law on its own, and also another concept, another drive, I would say, that's called more than Moore's, right? So let me write this down. It's also called more than Moore's. You can search this one online later on. So the first one, so the first one is called Moore's law. Oops, sorry. The second one, which we are now talking in the industry, is called more than Moore's. Okay, 2 things. It's not only about going down, technology, right? It's not only about scaling down everything, but it's also about using the Moore's law to do diversified roles, diversified functions with the technologies, okay, with the concept. So you can look into this online later on. It's Moore's now. So that means, for example, if you talk about Silterra, since Silterra is not able to go below 110 nanometer in terms of the equipment capability and stuff like that. So Silterra is good at diversifying different at a higher technology node level. For example, you can instead of going for CMOS manufacturing, you can also do sensors. You can also do photonics. You also do some other devices which require operate at very low technology. So this is called more than Moore's law. Okay, so it's about diversifying the function, diversifying the devices with whatever capability that you have. Okay, so it's called more than most. Then we also learned about high K dielectric, and then you now understand what is the role of the dielectric in the device, and then why going for high K dielectric is important in order to increase the gate capacitance and in order to minimize the leakage and in order to increase the current as well. So we've learned about different materials here in the figure with higher and higher dielectric constant, okay, the band gap that can be stacked on the silicon in order to perform as a high K dielectric. So in a nutshell, almost finished. In a nutshell, so you learn about the physics of semiconductor materials and eventually apply the physics to semiconductor devices and try to understand how the operation of the devices can be related to the physics. Okay, for example, controlling the channel length and then the mobility of the carriers, recombination in the device and stuff like that. Well, we have tons of different physics concepts that can be used in the semiconductor devices. And you also learn now that you need to use different, you might need to use physics concept or physics fundamentals to different devices, okay? Because not every device use the very same concept. For example, if you talk about a solar cell or lasers or LEDs, you need to go for PN junction, for example. But if you talk about a metal, semiconductor metal, MSM photodetectors, you might not need a PN junction at all, but instead just metal sitting on semiconductor just to do the photo detection process. So you need to know how to use the right concept for the right device. So group presentation you've done in the last 3 weeks. So good job overall. I'm so sorry again for group number 3 for recording. Okay, so based on this YouTube channel, you can always go back to the channel to revise later on, especially if when you want to be interviewed by the companies related. Okay, so this is really useful, at least for the past few batches. I've done pretty much the same thing on different platforms, and I've got good feedback from the past students, from previous students, because they can always go back to the files, to the presentation videos or whatever, to study the device, the operation, the device, the companies, at least to have some ideas of what else need to be prepared, and then you can move on to search for more details information. But in essence, this is a good start for you to have to come to a file and get pretty much everything there. Okay, so done with that good presentation. So next, please go to the teaching and learning assessment form online on eLearn, and then fill out the form. Okay, fill out the form to give your feedback on the course itself, and also to the delivery of the course. Okay, to the content of the course, and about me delivering the course, whether it's okay or not okay. Just be frank. Just say whatever you think you have to say. Just write the comments there. I'm okay with that. I'm completely professional. If you say it's a boring course, just say it's a boring course. If you say the delivery is not right or not interactive enough, just say it's not interactive enough. It's fine. I'll just take it professionally, nothing personal from the comments. Okay. So setakat ni just 2 based on the last few days record, only 2 of you, 2 of the 40 students. So please do so as soon as possible, because I believe the due date is coming quite near as well. So we need to have quite a strong feedback for every course that we teach. Okay, so please do so after the course. Thank you very much. So next semester, yeah, Mirun Hazi. Okay, thank you for that. So please do so for the rest 38 of you. Next semester, inshallah, I'll be teaching 47. If it's not changed by the school, but traditionally I've been teaching these subjects 386 and 47 typically, so I can follow your progress pretty much, because I teach you the fundamental physics and then the device, and then in 487 I'll be teaching you the process of how to do the device, how to fabricate the device. So for example, in 386, in this course we learn about the MOSFET, and then the device operation, device configuration. And then in the next course, we're going to learn how do we fabricate the MOSFET? How do you do the source and the drain? How do you fabricate that layer? How do you do the gate oxide? How do you do the gate on the gate oxide? How do you do the FinFET? How do you do the GAA FET? How do you fabricate solar cells? How do you fabricate LEDs? Okay, the 487 will be more focused towards IC fabrication, integrated circuit fabrication, which is mainly about Silterra, Infineon, and MIMOS, On Semiconductor, Global Foundries, Intel, TSMC, SMIC, and stuff like that. But the very same processes that you're going to learn in 487 can be extracted. In fact, they are more simpler to be used for solar cells, for SSD, for photo detectors. So the moment you learn 487, you know how to do other devices as well, indirectly, because the very same process, in fact, simpler processes, need to be extracted and used to fabricate other devices. So bila you belajar on ICs, you know how to use the process: lithography, etching, implant, fusion, oxidation, blah, blah, blah. Tons of different process can be applied to some other devices. So bila you belajar the physics, and then you belajar the devices, and then you learn about the process, so you know pretty much the whole stuff of semiconductor, I would say. So you have the fundamentals, the physics, the device, the process. So you know how does it operate, how does it look like, how to fabricate the device. Okay, so then you know the whole stretch of semiconductor spectrum. Okay, we're going to learn this next semester, inshallah. Okay, so you're going to learn about the lithography process, the etching, and how do you fabricate this Kirin 990 chip, for example. So this is pretty much the skeleton ataupun the building blocks ataupun the architecture. Kalau you pergi, if you go into a new city, if you say you fly to New York, if you fly to Sydney, if you fly to Tokyo, Osaka ke, then you akan nampak building kan. Bila you jalan on the street in the city, you'll see buildings and everything. So if you look at this figure on the right, this is pretty much it. You nampak macam building lah. Okay, and then you might see bridges connecting two or more buildings. So this is pretty much the building blocks of the IC in the phones, in the laptop, in the iPad, tabs, or whatever. But instead of seeing building, you're going to see the structures of your semiconductor devices. This is called interconnects. Okay, metal interconnects. You akan belajar aluminium, copper, how do you lay them like that in this way with the right size in order to ensure the device is operating at the right speed. For example, you not make sure your processor is operating at 3 gigahertz or more gigahertz. So you need to have certain building blocks to ensure those. And one of the key processes in this is lithography on the left-hand side. Boleh nampak kat sini, this is called extreme UV lithography, okay? EUV. This is the one that's costing 100 million USD per piece, okay? The size is about one bilik tutorial or so lah, ataupun 3/4 or so for one piece, and you need at least 20-30 of those in a production line. And this is only for lithography process, not talking about other processes yet. So that's the amount of investment that you need. So pretty much about 20 billion USD per fab for a new fab for advanced technologies to produce a single chip in your phone, in your computer right now. So, okay, we are pretty much done. My approach is simple. I rather teach students on how to think than what to think. It's not that I don't teach you what to think. Of course, I teach you what to think. But if you're talking about what, you can just go online, YouTube, and then you can find so many what's the information. But how to think, how to connect the information, how to filter the information in order to answer the right question, in order to scope your knowledge, in order to deliver certain tasks and everything is more important. So that's why focus on how to think. Connecting the stuff is more difficult than knowing the stuff. Okay? Macam you buat FYP lah, for example, you know the characterization of this and this, but how are they meaningful? How do you connect each other is more meaningful, okay? It's more important. And my final quote here for you is, knowledge cannot be pushed into a brain. It has to be pulled in, okay? I'm just a lecturer talking to you, teaching you the stuff and how to think and everything, but I cannot force you to learn, okay? I can run tons of different WebEx sessions to teach you, but if you don't want to learn, if it's not up to your own initiative, you won't learn. Simple as that. So you will understand this more if you go into your job later on. You will learn that it's not really the stuff you know, but it will be more of the initiative that you take. If you are the one that is self-driven, you take more initiative yourself, you will excel more in life. Okay? So it doesn't matter how much you know. So knowledge cannot be pushed into the brain, it has to be pulled in. So it's initiative, it's your own intention, it's your own willingness to learn. Okay? So this will persist in your career later on. So I don't want to teach you for the sake of passing the course only. Of course, I want you to pass the course, but it's for your life after university. So yes, that's all, guys, for 386 this semester. We have done all the 15 weeks in the course. Thank you very much for bearing with me for the past 15 weeks. So do you have any questions before we have a pick together? Right, can you please turn on your videos now? Okay, more, please, more. Now saya kat tepi ni, so bising sikit, it's fine. Come on, turn on your videos now. I think we can go up to 25 per screen. I'll go for 2 screens, then kita can shoot 2 kali lah. It's like a studio photo shoot, more or less, just for the memory. So I'll not be meeting some of you, right, next semester, because I think pure physics will not be taking 47, and I think medical physics as well will not be taking 47. But I'll meet about 20 of you, 20 plus of you in the next course. Okay, more, please. Turn the cam. Let me turn the screenshot. Sementara menunggu you turn on your videos. Okay, Dayang, mana Dayang? So who else not on? Darwina, Faris, Noor here. Noor's here. Which Noor? I don't know. Shafia. Okay, Pop well and board. Okay, that's fine. That's the result of too much lockdown, I think. I've grown my hair as well. Kat belakang ni agak panjang sekarang. Got a long time without a haircut. Okay, so sekarang semua on ke? Okay, coming up. Shreyas coming up. Faris, Noor, Shafia. Ada 3 lagi not on. Sri dah. Okay, good. Okay, ada 3 lagi belum eh? Are you guys okay? Or you have a camera problem? Siapa Pogba? Who is Pogba? Sorry Pogba, you are out. Sorry Pogba, you are out of Euro now. Okay? Nah, saya akan screenshot the screen, then I'll send to the group. Okay? Kalau you nak tangkap dengan you punya phone, then it's okay. Okay, so now let's be ready. I'll screenshot the whole screen. Kita buat 2 kali ya. Because it can only fit 25 per screen. I'll go later on. Okay. Okay, let me go to the first screen first. Okay, semua dah ready ya? Dah pakai bedak semua. Okay, so senyum saya akan capture the screen. Kalau nak ambil gambar guna form ya, okay juga. Okay, 1, 2, 3. Okay, I'm done with 1 screen. Hold on. Okay, I've got 1 screen here. Hold on, let's move on to the second screen. Okay, let me get the second screen. So another 25. Okay, 1, 2, 3 ya, ready ya? 1, senyum. 1, 2, 3. Okay, saya check ya. Takut nanti tak ada pula gambar ni. Let me check for a while. Hold on. Tak ada gambar, tak ada habis lah memory. Screen hunter, give me 10 seconds. Let me check the picture. Okay, hold on. Okay, let me confirm. Okay, I've got the first one. Got the second one. Yeah, everything good. So you ada siapa-siapa nak ambil gambar lagi ke? Last shot before the final class. Habis lah. So saya ambil satu lagi dengan phone. Tadi saya guna screenshot, capture screen. You ada kelas ke? So 11:04 already. Okay, let me get phone. Freestyle. Okay. Next screen. Okay, last one. Okay, second screen. Okay, freestyle. Sekali lagi. We're done. Right, so you like to say? Or you have another class to go? And this share kat group. This share kat
Tak ada apa.
group.
Cuma nak ucap terima kasih Dr.
Me. I would like to wish you anything. Okay, okay. All right. So I would like to wish you all the best. Okay, go ahead. Okay, thank you. Welcome. Okay, welcome to all of you too. Yeah. Next time, kalau apply jumpa lagi lah. I think about 20 plus of you applied. So for us and for all of you, in fact, all the best in your exam ke kalau ada, in your test kalau ada, in other courses, and then next semester as well. So you going okay. Nanti you akan go for your internship in March, I think, next semester. So December, January is a good time for you to start applying for your internship. The right window will be around December. Nanti during your break, just look into which company you plan to go for. And one from. Can you hear me now? Okay kan? Okay, right. So based on my interview last week with our students at JA, 4 students, so we have received good impression from the company. Okay, and some of the bosses even said that our physics student know more than the engineers. Okay, because you learn. Yes, really. I can see your expression, Alia. Because the beauty of being a physics student is that's fine, that's okay. You learn the fundamentals, you learn the device operation, and then you learn pretty much the physics, the inside of the device. Kalau you ambil engineering course, I'm not against engineering, even though I graduated with engineering degree last time. You learn mainly the circuit level, system, the device, and beyond the device. You don't know pretty much the inside of the device. Mungkin belajar sikit-sikit lah, the physics and everything, but your privilege here being a physics student is you learn the inside a lot. Okay, so then bila you boleh relate with the application outside the device, outside the physics, beyond the physics punya wall, you have the privilege of knowing the inside a lot more. So the impression I received from the boss is they like physics students, they want us to send more next batch. Okay, that's a good thing. At least for JA Solar, with interaction with me, they ask for more physics student next batch. So if you're interested in solar, then you can let me know. We can discuss, of course. So you have the beauty of knowing more than the engineering student, especially on the inside of semiconductor devices. Okay, so that's all I can say. So that's the privilege. Don't feel underprivileged. You bukan engineering student ke, semua nak engineering background. No, there are some industries looking for physics student in particular. Tapi mungkin not across the board lah. Cumanya you ada you punya own privilege in certain industries. If you talk about Silterra, for example, let me take about 2 more minutes. Sorry, dah terlebih masa. Silterra ambil, I think 10 or 11 physics student, pure and applied, if I'm not mistaken, this batch. And they asking for more. They're asking for more physics student to do the device integration, the modeling and stuff. And some of them are already absorbed as a fab integration engineer, device engineer, already halfway or close to the completion of internship. So that's the impression that we receive from our program. So that means our programs are good. Okay, so to give you a good assurance. So don't feel underprivileged. Just do whatever you have to do, polish your knowledge, polish your skills, and be ready for the internship interview and later on for your first job. Okay, so all the best to you. I'm sorry for any mistakes or everything. Kadang-kadang line the problem. If my delivery is not good enough for you, I tak faham and everything, I couldn't entertain everything, and I couldn't accommodate everything in the course. I'm so sorry. I apologize for that. I just didn't have enough time to feed you everything. And learning at universities is not about feeding you with the information. It's just about giving you what you have to know at the basic level, and then exploring to the rest of the stuff, branching out, stretching the knowledge is all new. If you can stretch knowledge, you can survive more, you can excel better in life. Just like what I have shown to you in your test 1 and test 2. It's about stretching what you know to the new stuff. Okay? Okay, bye-bye. Take care. Assalamualaikum. And take care. Stay safe. See you again next semester, insyaAllah. Kalau ada peluang jumpa face-to-face in the university later on, insyaAllah kita akan jumpa lagi lah. Kalau masih online next semester, then I don't know, maybe you'll see each other in like 3-4 years face-to-face. Kalau tersempak kat mana-mana. Okay, bye-bye. Take care. Assalamualaikum.
Haris rambut belah tepi elok.
Siapa? Haris? Nama baru ke?
Dia buat fashion baru lah ni.
Oh, okay. Alright. Okay, bye-bye. Take care. See you later.
Thank you.
Assalamualaikum.